All right, so let's take a look at the exercises from 5.3 part 2 that are on WebAssign. So look at this first one. Well, first off, I guess these are all really, or I guess the main idea here is centered around the second fundamental theorem, the capital F of B minus capital F of A business for evaluating a definite integral. And this first one is relatively straightforward in the sense that, well, like we always do whenever we're trying to evaluate integrals such as this, we're simply trying to find the capital F function, or rather a capital F function, an antiderivative of our function, for which we're considering the signed area between its graph and the horizontal axis, and then evaluate it 0, and subtract. And so here, right, I mean, this is just a polynomial. Apply the power rule to each of the terms, and then you'll have a capital F function. Throw in +0 if you must, but ultimately you don't even have to add in the constant, because whenever you evaluate that capital F function at 1 and that capital F function at 0 and subtract, whatever constant you would add would cancel out. So that's about as straightforward as they come. Looking at number two is fairly straightforward as well, although it involves a square root, which is mildly thorny in the sense that, remember, whenever you deal with square roots, when computing derivatives or antiderivatives, it's often easier to view them as fractional exponents. So I would just view this function instead of as square root x as x to the 1/2, and then you apply the power rule. So what, x to the 3/2, take the reciprocal of 3/2, which is 2/3, put it in front. So you have 2/3 x to the 3/2, evaluate at 9, evaluate at 4, and subtract. Classic application of the second fundamental theorem. Okay, so here's a fractional exponent that's just flatly given to you. So all you got to do here is apply the power rule, add 1 to the power, just keeping in mind that whenever you add 1 to -5/6, make sure you have a common denomination of sixths when doing that addition. So adding 1 to this is in fact adding 6/6 to that power, and then the rest of it plays out. When you're doing the evaluation, remember the 6 in the denominator has the effect of the 6th root. And so whenever you are evaluating at 64, the first thing you're going to do is take the 6th root, which I think is 2. I think 2 times itself, 6 times is 64. Right. Moving on. Actually, this was one from our Q&A today. Remember, E is just a number. At the end of the day, E is sort of just a number between 2 and 3. As it turns out, it's just the base of an exponential function that would be its own derivative. But in this case, we don't even have an exponential function. There's not even x involved. So for all intents and purposes, you might as well think of this as integral from -6 to 6 of 10 dx, where the antiderivative would be 10x. In this case, the antiderivative would be just ex. What about here? Well, here, this is this classic situation where when you see a quotient inside an integral, it may give you hesitation because, boy, how in the world are we going to find a capital F function when the quotient rule for derivatives was bad enough and the quotient rule for antiderivatives really doesn't even exist? So how are we going to proceed? Well, perhaps the best way to proceed is just to take that x to the 1/2 that's downstairs and divide it by each of the things upstairs. That way you can get rid of the denominator completely. The 6 will have a power x minus 1/2. Take 1/2 away from 2 and you'll get 3/2 for that power. So hey, now you would boil down to something that would just be sort of polynomial-like. And then the evaluation, of course, would be an application of the second fundamental theorem. So looking at this, let's see, we'd have 6x to the -1/2. Oh, it's got to be this one because that's the only one with x to the -1/2. Yeah, and so then how do you find the evaluation of that integral? Well, now you're going to have to actually find the capital F function, because the act of dividing by the x to the 1/2 that's downstairs is just algebraically restating the function that was inside our integral to begin with. The act of actually computing the integral of finding the capital F function would then be adding 1 to the power and taking the reciprocal of that power and putting it in front. Right. So here's, classic example. We got a polynomial term, nothing to sweat there. And I suppose this sort of feels a little bit like a polynomial term, but you know which function has a derivative of 1 over x. That would be ln x. But just remember ln absolute x, just to be exceptionally precise. I guess in this case, we're evaluating at 1 and 5. So I suppose ln absolute x, excuse me, is not necessary, but it is proper form. So it probably would be good to include at every step along the way. I get the capital F function here, or at least a capital F function, to be x squared plus ln absolute x, Of course, you could do x squared plus ln absolute x plus c for any c, but when you evaluated 5, evaluate at 1 and subtract, those c's go bye-bye. Let's see next. Oh, right. We also talked about this one during our Q&A today. This is really just a memorized fact, but anytime you're trying to compute the antiderivative of a function, the first thing you might ask is, well, what function has a derivative of that? And that's exceptionally wise because we don't have a product rule for antiderivatives either. So that'd be real kind of tricky to work out otherwise. But we do have a function whose derivative is secant tangent. The capital F function here is actually just the secant function. You're going to have to evaluate the secant function at pi over 6. You're going to have to evaluate the secant function at 0, which is going to require knowledge of the unit circle. So that's going to drum up some thoughts from your past. If the unit circle is rusty, now's a good time to remind yourself of the unit circle, because if something like this is in play for the homework, something like this is in play for the test, and on the test you don't get a calculator. So yeah, you're gonna have to be able to do secant of pi over 6 and secant of 0 from scratch. Oh, this one is another one that's kind of mildly annoying. Remember, e is just a number, so this might as well just be x squared, although it's not x squared, it's x to the e. So increase the power by 1, put the reciprocal of that in front. So I think that first term becomes 7 over the quantity e plus 1, x to the e plus 1. And now the 8e to the x, this is the exponential function e to the x, whose derivative is itself, whose antiderivative is itself. And so the antiderivative of 8e to the x would just be 8e to the x. Evaluate at 1, evaluate at 0, subtract. This is another memorized fact. When you see the square root of 1 minus x squared in the denominator, that is a memorized fact associated with the sine inverse function. So here, the 3 could factor out, or you could think of the 3 as just coming along for the ride, as constant multiples do when computing derivatives or antiderivatives. So the antiderivative here would just be 3 sine inverse. Evaluate at the top bound, evaluate at the bottom bound, remembering when the sine inverse function evaluates, you're working from ratio back to angle, but the angles of the sine inverse function are between pi over 2 and minus pi over 2. Incidentally, that won't come into play here because we have positive ratios, which would put you in quadrant 1. But ultimately, the sine inverse function does evaluate angles in quadrant 1 and quadrant 4. In quadrant 4, you use the negative angle. Just a quirk of the sine inverse function. I hope something that's that niche and trigonometric wouldn't come into play in a future exercise set. But well, there we go. Moving on. Oh, this is the piecewise function here. We talked about this in class. This is a function that has different behavior on different intervals. So just break this integral into 2 different intervals. If you're concerned about the fact that this second piece is between 0 and 5, not including 0, don't be concerned about that, because the area between 0 and 5 will be wholly dictated by this function, 25 minus x squared. The behavior at the endpoint is actually irrelevant to the area. If you think about it, the endpoint x equals 0 has no width. And so when you're breaking this integral down into a pair of integrals, one between minus 5 and 0, and the other between 0 and 5, you are going to take the 2 functions of interest, one in each of those integrals. And for the integral between 0 and 5, you will use 25x minus x cubed over 3 as the capital F function to evaluate, because, again, that endpoint x equals 0 is not going to influence the area under the function 25 minus x squared between 0 and 5, because that endpoint has 0 width and is negligible to the area contribution. So, right, an appropriate way to think about this type of situation is that the values of a function at its endpoints are not going to affect the value of its integral. The value of its integral is going to depend upon the values of the function along the meat of the function in between the endpoints. Oh, this is silly. That's just replacing x with z. I mean, it's the same function. It's looking at the same variable with respect to it. Same function, same variable with respect to it. So this would just be capital F of b minus capital F of a. And this would be capital F of b minus capital F of a. Of course, those are the same thing. If f is continuous, oh my gosh, what have we done? We've taken an x and factored it out. No, that can never be, because x is a variable. You can factor out a constant. If that x were a 10 and just 10 always, fine. But that 10 is not, that x is not 10 always. That x is equal to a when x is a, that x is equal to b when x is b. That x is varying, and hence some other technique or tactic would need to be employed. In fact, I think the technique or tactic is going to have to wait until the first midterm, because It requires a fancy integration technique that's not even worth discussing at this point. But yeah, long story short is if x were a constant like 10, factored in and out. If x were e, just a number between 2 and 3, factored in and out. But x is not just a constant, so we mustn't factor it in and out of our integral. Oh, but yeah, right on cue, right? 2 is just a constant. Of course, you can factor 2 out of an integral. No sweat. We've discussed the geometric reasons for this, right? Because 2f of x just doubles the height of every rectangle in your approximation, or just doubles the height of your area region, thought of not even in terms of rectangles. And so that would, of course, double the signed area associated. Right, here's another fact which we saw, which is essentially to say, if you take two functions and look at their sum, the area under their sum is just the sum of the areas under each of them. We saw this also whenever we were looking at properties of the definite integral. I think we looked at like x squared plus 5 or something like this, and the area under the function 5, the area under the function x squared, sort of just like tack one on top of the other, and that gives you the area under the sum of the two functions. So this is always true. In fact, this combined with the fact above was why we started to think, maybe derivatives have something to do with integrals, because integrals demonstrate properties that derivatives do. Constants factor out and they distribute across sums. Oh, this is a severe no-no, right? I mean, the derivative of a product is not even the product of the derivative. So why would the antiderivative of a product be the product of the antiderivatives? That seems quite egregious. And yeah, this is way off. There's in fact no product rule for antiderivatives. So there's no way to even make a statement about this in general, frankly. Well, not without it getting muddier than what the original expression was. This feels false too, because why can we factor out the square root x? I mean, plug in a function like f of x equals x into this, and I bet it turns out to be false, because x to the 1/2 here would be what, 2/3 x to the 3/2. And if you took the integral of f, that would be x squared over 2. If you took the square root of that, that turns out to be just x over square root 2. Yeah, those are totally different functions when you look at capital F of b minus capital F of a. So this just feels egregious. To why can we factor a power? Because right, a square root is basically a power of 1/2. Why could we factor a power out of an integral? That feels heinously abusive. You can factor a constant multiple out of an integral, but why can we factor a power out? That's a little wild and crazy. So, right, that's my take on all of these, and well, that's a video.